Okay, I'm going to assume that this is working and this is going live. Last time, earlier today, I did a stream directly on Twitter and Periscope, but I thought for this particular one, I'll try doing it on Twitch to see how this platform works when it comes to streaming. So I'm just going to check that everything is working fine because it's the first time that um, I'm trying Twitch. So let's see if this is working. Just confirming, and yeah, it seems to be working a okay. Okay, so what we're going to be doing, or what I'm going to be doing for this session is basically debugging what happened in the first session. I had some problems, and I think I found a solution while I was having lunch and having a coffee. I think I realized what went wrong the first time around, particularly when it came to checking the linear models. So we're going to go through it again and see what we can do about fixing this up. To give a refresher, I'm basically going to be creating synthetic data sets in order to approximate real data sets, as I mentioned before. If you've got any questions as well, please contact me over Twitter. And you can also look at my blog post on the bottom right, and you can actually see what I'm actually doing and why I'm doing it. But to give you a very, very quick summary, I'm looking at a way of creating synthetic data sets which can encourage how we can share data in science. And this is really important so we can actually reproduce and understand what other people are doing. But of course, particularly if you're working within the clinical realm, which is where I work, of course, there are a lot of considerations when it comes to data privacy. You can't just go posting people's data. So by creating synthetic data sets, this is a way around doing this. Of course, it's not the real data, but because these data sets share the same relationships and the same data structures as the original data, you can get a very good idea of what the original data is like. So what we're going to do is we'll just go through and reload everything. We're loading our data set, which is a data set looking at the impact of intranasal oxytocin administration on feelings of spirituality. In short, half the people were randomized to getting a nasal spray of intranasal oxytocin and half got placebo. And about 45 minutes afterwards, people were asked, how spiritual would you consider yourself on a scale? I think it's from 1 to 7. And a few other measures were collected, but this was one of the main outcomes. Let's take a look. Okay, so we're going to import that. And then what we did as well before is we did a basic t-test to look at the difference between the reports of spirituality between oxytocin and placebo group. So we'll run that t-test again. Okay, as we can see, a t-value of 1.14, and then we have created our equivalent linear model, the equivalent linear model of a t-test. We'll run that again, get the summary, and we can see that the results are exactly the same. So when it comes to actually comparing the linear model against the real model, in session 1, I think the mistake was that I was comparing it against a smaller data set which only actually included 4 or 5 of the variables. Now, the way that SynthPop works is it looks at the interdependence between the whole set of variables that you have. So by only doing a subset of these variables, I was comparing apples. I was comparing apples with oranges. I'm just going to see how that stream is going. I think it seems to be working fine. Okay, so what we're going to be doing here now is yes. Okay, so we're running our linear model here, and we are doing this on our simulated dataset, which we created up here. And let's compare these two. See what the plot looks like. Zoom in. All right, that looks a lot better. That's kind of, that's more what I thought. These are very, very equivalent. Okay, now let's just confirm and run this again. Looking at the anchovers. And we're going to compare against okay. A little bit of a difference there. See what we can do. Compare these two. Yeah, these are pretty similar as well. Okay, so our synthetic data set is OT_sim, which we created earlier up here. Try this again, change that. Okay. Run that again. These are real similar. How do they look? Yeah, cool. Okay, so this data set now is looking pretty good. But now what I want to do, this is a data set that I'm already pretty familiar with, but what I want to do is I want to find some new oxytocin data sets. I want to see a range, this applied to a different range of data sets. So what we're going to do is we're going to go to Google dataset search. There we go. Search for oxytocin. Okay. We'll see if there's anything that's particularly relevant. Let's check out this one. All right, how good is dataset search? Let's have a look. Oxytocin single nucleotide polymorphisms, or SNPs. Oxytocin levels and empathy. This is a pretty normal. Okay, so it looks like we have a data set here. Let's take a look. Loading. Taking a while. All right, I'm just going to download them. let's call this OT snip blood. We'll save it as a CSV. First, let's have a look at what it looks like. All right, here is the data. So we've got participant number, EQ, emotional quotient, I'm assuming, RMAT, which is a common test, reading the mind and the eyes task, which is a test of theory of mind. OT measurements, those are incredibly high, so I'm assuming they did not extract their samples, and some 2 different oxytocin receptor SNPs, the alleles for the SNPs, and the sex of the participant. Now let's save that as CSV because it's easier to deal with within R. There it is. All right, let's go back. Import dataset. That should work. Call the file OT blood. Okay, file looks good to me. Yep. OT blood dat. OB dat. Might be a bit shorter is better. Okay, there we go. Blood. So what we want to look at is the relationship between oxytocin, peripheral oxytocin concentrations. Let's look back at the description. The influence of 2 SNPs on empathy quotient, RMAT, oxytocin levels, picograms per mil. Yep, those levels are extremely high. There's no description of how the blood was collected, but I'm assuming it was an ELISA. And we have some high blood levels. Male and female. Okay. Let's comment. Blood oxytocin concentrations. Trying to figure out a way to get some background music for this, but it's harder than you'd think. And apparently you're not allowed just to play Spotify because you don't have a license to distribute the Spotify tracks, which makes sense. Okay, we're gonna go back to the old correlations, which were right above. First, we'll create the synthetic data set. Okay, create synthetic data set. Just keeping an eye. Twitter. Okay. Paste that. Set the seed again. Creating OBSIM. Let's paste that in so we don't forget it. I know it is bad form to download a file directly from the downloads. I should move it into the project file, but I can do that another time. BDAT OBSIM. Okay, we are set the seed, run the synthesis. Those are the old variables, so we don't need that. We are comparing OBSIM against BDAT. Let's just have a look, see. Oh. Okay. Soon that'll bring up those updated plots. Or maybe not. Let's try again. Okay, that seems to be working. Let's see how the distributions compare between the simulated sets and the original data set. While we're waiting, we'll comment. Okay. It looks pretty similar when it comes to EQ, RMET. RMET, someone scored very low. RMET ranges from 0 to 36. Anyone scoring above 28 is doing extremely well. I use the RMET in my PhD thesis and in a lot of my research, and you basically show pictures of faces around the eye region and ask people what they're thinking or feeling. It's a really good way of discriminating people with social difficulties, such as with autism or schizophrenia. On average, people with autism or schizophrenia tend to score around the high teens, but neurotypical individuals get around the mid-20s, which is what we got here. And things look pretty good in comparison, and same with the blood levels. Got some zeros in there. I'm not sure why we got some zeros. Maybe that's an NA, but it's worth keeping an eye on that. And the EQ looks fairly well similarly distributed. Okay. Going to compare correlations. A good thing about we've done the correlations before for this other data set, so I'm just going to be using the same code and adjusting it. Call it B core for blood. BDAT. What did they call that? OT, and we'll look at the RMT first. OT. Try this. So what I'm doing is I'm confirming that the linear model version, which we've done through this very, very nifty guide for creating alternatives or linear model alternatives to common tests. So we'll run this. Run it again. What on earth is this taking so long? Okay. Yeah, that'll do it. Correlating a variable upon itself. That's why. All right, p-value 0.46, correlation barely 0.1, so not much going on there. On the relationship between peripheral oxytocin levels and RMET, which doesn't mean much because peripheral levels during basal conditions don't really correlate with central levels in the brain of oxytocin, so that's not much of a surprise there. Run this. Minus 0.2, minus 0.734. Minus 0.734. Bang on. Okay, those are the same. Let us run the correlation scale. OT. RMET. Data equals BDAT. So this is the synthesized version. So you would expect the results to be similar to the original version. Let's run this. Something's gone wrong. Yes. Data. Blood. Got to run it on the synthesized data. Let's try it again. There we go. Now let's compare the two. Compare this against the original dataset, which was B core. No, BDAT. Okay. Didn't do very well. Let's see how we go. It'd be worth looking at. Just gonna have a quick look. I do remember. Okay, there is that very low value. Let's try the same thing with RMET. Sorry, with EQ. Copy and paste. It's probably a better way. EQ. No, that's wrong. OT against EQ. OT against EQ. Run that correlation. Yeah, 0.9, so the correlation is even smaller than RMET. And we'll see and confirm that we get an equivalent T statistic of 0.098. 0.098, there we go. We are good. EQ. Running our synthesized. we'll compare this. Have a look to see. Okay, this actually looked pretty similar. I want to look back at the datasets again. There's that one value there, which seems to be a bit odd because we get that in the observed dataset, but it is not shown. But you wouldn't expect that. You wouldn't expect that to have an impact on the final results. Just label this. Just going to compare these two things again. It's a little bit unexpected, but maybe it's just maybe this data is actually not very well suited, and that is it's important to discover. I'm going to try one thing. Should not make a difference trying this, but yeah, thought not. Minus 0.73. It's quite a difference there between the simulated set. I'm going to go back into the documentation and have a bit more of a read. What happens if we actually try this? Create 5 simulated datasets. See what happens there. Yeah, it doesn't look great. When you actually that looks much better when you're working with the EQ measure. But again, it's a bit of a concern there that the number of simulated data sets has such an impact. Maybe you actually need to do that. How big is the data set? 74 participants, so it's okay. Not great, but it's okay. Okay, let's try that. Create a summary. Okay, so this is creating the average. There we go. All right, so the original data set has the lowest value of here of oxytocin is 15.6. Whereas the synthesized is 85, mean 35. Shouldn't make that much of a difference. But here we are. This is a good point. If the models used for synthesis truly represents the process that generated the original observed data, an analysis based on the synthesized data should lead to the same statistical inferences. we run correlation test on the synthesized data? I don't think so. Let's find out. No. But you can run inferences on the simulated data. To compare the synthesized variables with the original ones more easily, compare function. Let's try this. Okay, so then you can specify against the mean. Let's try that. And then let's see how it goes by doing this. It's always good just playing around with the data. Not playing around with the data, but playing around with the package. Yeah, what's interesting is it seems like for that low value, although it was observed in the original data set, only 1 out of 3 have done something similar. Let's try 1 to 5. Okay, so look, if you average those two, then you're actually going to get pretty close. But let's go back to the documentation. All right, so returning to the original. Summary of the fitsins object. Just comparing these two things together. Warning, note that all these results depend on the synthesis model being correct. Okay, so it's okay, but not great. We bump it up to 10. What happens there? It takes a bit more time to process, but maybe we can get greater accuracy. That looks good. Okay. Yeah, it's not much difference. Not much difference if you actually increase that. So seems to be some limits there. Just checking another bit of documentation. Once again, could it be something as sensitive as the seed? can't be right, but let's find out. This is good. By playing around like this, I'm getting a better idea of what the package actually does and what the limitations are. Yeah, once again, it totally misses these ones. And if we bump this up to 5... see what happens. Try again. It's handy getting a visualization here. Okay, that seems to have performed a bit better. Seems to be quite sensitive to this outlier. All right. My brain is fizzled, so I think I'm going to take a break and I hope we'll be back tomorrow getting a better understanding of why some models seem to work quite well and others don't. So I'm going to sign off for now.